start the recording there. Yeah.
It's cheap that most of the sciences do.
Well, and we're going to keep all our decimal places until the end anyways. So it's just like a rounding rule. So it's not really, I don't know. But I don't want to say it's not important because it is for you guys. But for me personally, it's never been important. I know that's so helpful. Oh, one thing that I wanted to just mention is for formula sheets. So I haven't given you a formula sheet. I'll give you kind of a rough go of it. But what we're going to be doing is you're just going to have a blank piece of paper and you can just write your own formula sheet, right? Sounds great, right? But it's actually a lot of work because you have to figure out what you need on your formula sheet. But I do find it's pretty helpful because by the time you've figured out what you need on your formula sheet and you've written it all out carefully so that you have enough room for everything, you've pretty well learned it, right? And so, so that's a good thing. But so you will be kind of constructing your own formula sheet. And I'm telling you this now so that you can start kind of highlighting things that you think you might need on your formula sheet now. For example, sig figs, we'll kind of, I guess, circle back to them. But things like maybe what we were doing the other day, what were we doing? Exponents, for example, the rules for exponents, maybe stuff like that isn't quite as fresh. And so right now you might need that on your formula sheet. And so what I would say is maybe have an evolving formula sheet, right? As you kind of have things ingrained, you can take it off your formula sheet and make room for new stuff, right? But it's always kind of good to keep track of things that you haven't quite learned yet, right? And that you think you need as a crutch. And that's, I mean, that's good to know, right? As a learner. So I'll just make a note here. Oh, my silly pen. So you will write your own formula sheets for this course. What's this, 8.5 by 11? Is that just a letter size piece of paper? On a blank 8.5 by 11 page. And I can get you blank paper if you need. I'll just steal from the printer. Okay. But yeah, so maybe start thinking about what would I want on my formula sheet, right? And just kind of go from there. Okay. And you can, I'm not going to check that, you can have basically whatever you want on there. So if you want a fully worked out problem, go for it, right? It's kind of up to you to decide. All right. So we're going to keep going through this one. I think was fine. We're going to keep going through that worksheet. Paste it here. I'll say worksheet continued. Now, for the next 4 parts, this will all be for review on the scientific notation worksheet. Remember I was showing you where the extra practice problems were? So for question 4 and 5, those are all practiced on the scientific notation one, of course. Scientific notation, the only thing that I saw happening was we have to have just one whole number and then the decimal, right? So we can only have one number. So if you're putting 10.4 times 10 to the negative 2 or whatever, that's not right, right? We'd have to have 1 times 10 to the 1. I think I messed that up, but anyways, I'll do it proper. So in this case, right, but overall, I didn't see any problems with the scientific notation. And so here, right, we're moving our decimal forwards. And so I just kind of bounce it forwards. And so here, 3, 6, 9, and then 10, right? So it goes boom, 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 boom. Oh, got messy. And then boom. There's more than 10 booms in there. So then here, 6.264 times 10 to the power of 10. Right. And if you're moving your decimal the other way, you just have a negative power on the 10, which we'll be doing in the next part. So here we're moving the other way, but almost as many booms. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we have 4.5 times 10 to the power of negative 9, right? Moving it in the opposite direction. Cool beans. Nice. Question 5 is where we kind of kick it up a notch, where we're multiplying and dividing with scientific notation. Notice though that we're just multiplying, right? 12.4 times this times 9.1 times 10 to the power of 3, right? So when we're multiplying through, we can actually rearrange these and kind of collect these like bases of 10, right? 10 to the negative 5 and 10 to the power of 3. Now we're dealing with exponents just like we were last day, right? Where we can combine these exponents and not have to deal with it. Of course, you can probably just do this in your calculator, right? But I want to show you how it works if you just want to do it kind of by hand, right? Sort of by hand. Okay. 12.4 should be 1.24, right? But I don't know. I just stole it blindly. It's really biting me in the butt when I steal things blindly. So anyways, trust no one, including myself, I guess. So here, if we rewrite this, I'm going to rewrite this as 12.4 times 9.1. So I'm going to group the powers of 10 together. So times 9.1, and then times 10 to the negative 5 times 10 to the power of 3. Because what we said was, okay, well, these two guys have the same base, right? And so we can combine them and rewrite this as, well, we can do 12.4 times 9.1. That one's not going to change. Times 9.1. 112.84. And then times 10 to the negative 5. And then I'm just going to write plus 3, right? Because I'm combining those powers of 10. So then I have 112.84 times 10 to the negative 2. What I'm going to do is I'm just like going to write 112.84 in scientific notation, because then I get another power of 10 out there. And then I can make sure that I'm dealing with these powers properly. So 1.1284 times 10 to the power of, sorry, 2. That was just a scribble. 1, 2, yeah. And then times 10 to the negative 2. Right? So I'm just swapping out the 112 with something in scientific notation. Okay. And now I can do the same thing. I can group these 10 to the 2 times 10 to the negative 2 and just have 1.1284 times 10 to the 2 plus negative 2. That's just going to go away, right? Yeah. Crisis averted. Okay. So then you have 10 to the power of 0. As a rule, anything to the power of 0 is just 1, right? And so we've got 1.1284 times 1, which is just 1.1284. Okay. Any questions about that one? Yeah. Nah. You'll always have your calculator. Yeah. Just to show you how you can manipulate it. This one here. It's from converting the 112 to scientific notation. Let me scroll down here. Move it down so I can actually reach it. So here, right, 112, I'm going to rewrite that in scientific notation, right? 1, 2. So then I'm swapping this number out with this instead because they're equivalent. Right?
I saw the whole thing as
yeah. Right. Yeah, I'm just swapping out numbers, doing what's, it's kind of like skiing, doing what's convenient for me. But yeah, definitely longer than you need to, but it's just the surefire way of doing it. Okay. Any questions about that one besides those two? No? Let's do the next one then. Oh, question?
The significant figure is now 2, so the fewest figure.
Well, because we haven't talked about sig figs, I ignored it. Yeah. But yeah, you're right. Yeah, I think it should have, the final answer should have less decimals. Yeah. But yeah, so I figured at this point, we haven't talked about sig figs, so I'm just keeping all my decimal, or as many as I can. But you're absolutely right. Okay, so for this next one, when I did the practice one, here's confession time. When I did the practice skills assessment for you guys, I was just running through it to see how long it would take me, just so it wasn't too long for you guys. And so I was trying to be fast, and I actually screwed up my power of 10 here. It's pretty embarrassing, but that's why I'm showing you the surefire way, so that you don't make the same mistake that I did. Although I'm pretty sure you wouldn't, but
when you're working on time,
sloppy.
You just do it and assume it takes us 3 times as long.
Yeah.
Okay.
It is, yeah. Yeah, I do. So whatever time it takes me, I multiply it by 3, and that's usually good for you guys. But with some mistakes, I guess. No, only one tiny mistake. Ooh, that hurts. Okay, so for this one, same idea, right? I can kind of pull the 9.2 and the 6.5 off to the side and deal with these 10s on their own, right? And so remember what we did for 10 to the power of 3 in the denominator? To move it up, we would just write it as 10 to the negative 3, and that's equivalent, right? And so here, what we can do is we can say, okay, well, I'm going to treat the 9.2 over 6.5 just as its own thing. And the reason we can do that is because we're multiplying, right? If we had 9.2 plus 10 to the power of 6, then we couldn't do that. Then we couldn't just separate things. Okay? But then times 10 to the power of 6, and then times 10 to the negative 3, right? Bumping it up to the top, we just make the power negative. So I can do 9.2 divided by 6.5, get that out of the way. 1.415384615 times 10 to the power of 6 plus negative 3, right? Combining those powers. And again, not paying attention to sig figs, because we're not there yet. So now our final answer, 1.415384615 times 10 to the power of 3. Voila. Yeah, that's fine. Yeah. I think as long as you have like 1.4, it's fine. Even better. Yeah, any other questions about that one? So if you were already sticking to the rules of sig figs, that's great. But like I said, I'm not quite there yet. And I might have to push it off for a little bit. Talk to Frank, the boss. Frank and I share an office. I think you guys stopped by, yeah? So he's a pretty funny dude.
Yeah, I'm pretty sure it's just in whoever's class, like the instrumentation, he just wants it advertised. Read.
Okay.
I don't think it's like,
I'll grill him on the reasoning. If it's laziness. No, I'm not suggesting that.
now it's easy.
Well, he'd probably be the first to say it. Oh, this one, gotta move this over a little bit. This one's a different type of question, and so if you want more practice with the circles, then, but I think it was pretty good on the skills assessment, right? And so, but just have a look at area, I guess it's called area dash circles. So we're given that D is 10 centimeters. I'm dropping the units, even though I shouldn't. Can add them on at the end. Pardon?
That would be no marks and stuff.
No way, Jose. Am I losing any marks? Yeah. Yeah. What you will find is that I am really bad, because for me, units, I mean, whatever. But the main concern, you guys have met Rick, right? But do you guys have Rick this term? Oh, okay. So he'll teach you CAM, and he was like, if all you do all term is unit conversions, I'll be so happy. So he just really wants unit conversions, and so obviously in chemistry and whatever other field, units are really important, right? And so I brought some unit conversion practice sheets today, but we'll see how we do, right? So thank you for acknowledging that. So we're asking for the radius, the area, the circumference, even giving you the formulas. Isn't that so nice? So kind. Yeah, in case you feel like you might need those might be good to have. Because I won't always be so kind. Actually, that was Kate being so kind, not me. We'll start with the radius because we need the radius in all our other calculations. So the radius is d over 2, which is just 10 centimeters over 2, putting us at 5 centimeters.
We're just gonna have it showing that, right?
Yeah, I mean, something like this, no, if you just said 5 centimeters, that's fine. But in general, I've seen a lot of silly mistakes, kind of thinking errors. You know, you're stuck on the last question, now you're working on the next one, and you've got a number stuck in your brain. I know that happens a lot. It sounds silly, but it happens a lot. And so if at least you're showing me what you're doing, and then you're telling me that 10 divided by 2 is 7, well, this is right? And that's what I care about, right? I don't actually look at the answer so much as your thinking process, right? So everything that you're doing, even in your head, you should try to communicate to me somehow, right? Because I'm trying to follow your thinking process. And so I mean, if I see the right answer, then I don't bother looking at the rest. But if I see the wrong answer, then I'll follow through and kind of be like, oh, so how big of a mistake was this? Right? Was it a silly calculator mistake, or was it a conceptual mistake, right? Because those are going to weigh differently. Okay? And so definitely show all your work as much as you can muster is good. Okay? That might be a little overkill. But it's good. Let's find the area. The area is pi r squared. Took me a while to find pi on here. It's like way down here on the times 10 to the power of x button in the shift section, yellow section. So just kind of really tiny. So pi times 5 centimeters squared, I guess the centimeters isn't squared, is going to be, oh, well, I guess it is. Yeah, never mind. That was a silly comment. Like, hey, it actually works. So 5 squared. Did you guys find the squared button? It's just x to the power of 2, kind of easier. 25. So you've got 25 times pi centimeters squared. 25 times pi, oops, hit the wrong button. Is approximately equal to 78.53981634 centimeters squared. So, yeah. Again, not sticking to sig figs and things. And it's approximate because 25 pi is right. What's the word I'm looking for? Precise. C, the circumference is 2 pi r. 2 is just a number, pi is just a number, times 5 centimeters. 10 pi centimeters, which is approximately, oh man, how many digits of pi do I know? 3.14, I think, 15. There's a song, I don't remember it though. Anyways, I always just go to 3.14. 10 times pi. Hey, that S to D button is way better than the approximately equal to button. I know they do the same thing, but you guys showed it to me last day and it's really good. Really convenient, I should say. 31.4159264 centimeters. I think that one's pretty good. Any questions about that one?
You don't want us to do any of that.
Not for now. You'll await orders.
Remember the causes of problems and mistakes.
Oh. Okay, so question 7, you can look at unit conversions, which is actually the sheet I printed out for you. Stole it. This one you had to do on your skills assessment, but I think it was 3 kilometers into centimeters. Changed it to 4. Wow. You could probably just do it, right? But let's just look at what you're actually doing in your head. So you're saying, okay, 4 kilometers, you want to make it into centimeters, but you know you have to go through meters first, or you have to figure out how many centimeters in a kilometer, but that's trickier, right? Especially considering the conversions that I've given you. Okay, and so 4 kilometers, to get it into centimeters, you're going to have to first convert it to meters and then into centimeters, because you know that there's 1,000 meters per 1 kilometer, right? And so that's going to convert it into meters, right? But then you want to convert it to centimeters, and you know that there's 100 centimeters per 1 meter, right? And so how it's going to work, right, is, I'll just use a different color here. This kilometer is going to cancel with that kilometer, so now you're in meters. This meter is going to cancel with this meter, and so now you're in centimeters. Okay. And I know it sounds kind of silly, but this is the concept that Rick was telling me your predecessors have not kind of mastered, let's say. Okay, and so this kind of thinking that, okay, well, I can bounce through different conversions until I get to what I want, right? As long as you keep track of, okay, well, there's 1,000 meters per kilometer, right? There's 100 centimeters per meter. Then you can bounce through and you can cancel these units as you go, right? Until you end up at the unit that you want. Okay, and so, of course, there are formulas, but you don't really need them if you just keep in mind that as long as you're canceling appropriately, you can just get to what you want, right? Just kind of own your unit conversions, right? Because now we just have 4 times 1,000 times 100 over 1, or 100,000. Oops. Centimeters. Or if we have an equation, right? So a formula, right? Then in part B, we're converting 1,931 kelvins into degrees Celsius, and we know that the general formula is Kelvin is degrees Celsius plus 273.15. Not too bad. So then we know Kelvin is 1931 degrees Celsius plus 273.15. And so to solve for the degrees Celsius, we just have to move the 273 over. And so we subtract it from both sides. So we get 1931 minus 273.15 is degrees Celsius. And remember, I just like to have whatever I'm solving for on the left-hand side. And so I'm just gonna kind of swing door this and rewrite it as degrees Celsius is 1,657.85. Again, not paying attention to sig figs and things. Any questions about that one? Hey, fractions. You can see add and subtract fractions. To add and subtract fractions, right, you have to remember they have to have a common denominator, right? So you have to have a common value in the bottom. And there's lots of different tricks to doing it. I'll show you kind of my fail-safe one. But of course, if you look at these and you find the lowest common multiple, then that's great. But I'm just gonna stick to my way because I find that it's a lot less work. So what I do to make a common multiple, or a common denominator, sorry, I just multiply these two together, right? So I say, okay, well, my common denominator is going to be 6 times 2, so 12, right? And how do I get 12 in the bottom? Well, I have to multiply 6 by 2 and 2 by 6. But I can't just do that, right? Because I'm not allowed to change the makeup of this, right? But what I can do, if I have to multiply by 2 on this side, I can multiply here. I can multiply it all by 2 over 2. 2 over 2 is just 1, right? I'm allowed to multiply by 1, nothing changes, right? So that's legal. And so what I do is I just multiply the first term by 2 over 2, and then the second term I multiply by 6 over 6, right? Just to force 12 in the bottom, and then whatever happens up top, I deal with later, right? Once I have that common denominator, then I can smush them together and they just stay over 12, right? So we don't add the denominator, only the numerator, the top. Okay. But like I said, if you've got a way that works for you for adding and subtracting fractions, then that's great. As long as we get the same answer, you're good to go. Okay. Just giving you one way. So 5 over 6, I'm just going to rewrite it, plus 1 over 2 is the same as 5 over 6, and then I'll use a different color here, times 2 over 2 plus 1 over 2 times 6 over 6. Right? Multiplying fractions, you just multiply across, right? So 5 times 2, 6 times 2, and that's how we get that 12. 1 times 6 over 2 times 6. And so what we get here is 10 over 12 plus 6 over 12. Now we leave the bottom as 12, right? They're just getting smushed together. And so we've got 10 plus, 16 over 12. Only add the numerators. The common denominator stays the same. As long as you got to 16 over 12 or some version of that, you did it. Nice.
How far do you want us to go with it?
I'm just leaving it at 16 over 12. It's all the same number, so that's why I'm not too, I don't know. If we do the next one, if we apply the same rule, right, or the same idea, then we're multiplying 6 over 7 by 4 over 4, and we're multiplying 1 over 4 by 7 over 7. 6 over 7 times 4 over 4 plus 1 over 4 times 7 over 7. Six times 4 is 24 over 28. Plus 1 times 7 is 7 over 28. Combining these, we get 24 plus 7 is 31 over 28. So again, if you got that or some version of that same number, then we're gravy. Any questions about fractions? Combining fractions? Ah, the old SOHCAHTOA. So there's a sheet called SOHCAHTOA practice, as if that's not. A giveaway. Oh. I got lazy because, so I write my notes in LaTeX. I don't know if anyone knows LaTeX, but it's a typesetting language. And so to draw things like this is actually kind of tricky. But of course you just Google it and you steal someone else's code. And but that's why I decided to just have a general one and just tell you what they are, because then I can just swap out whatever goes where, right? And so filling it in, right, I told you the angle B is 17 degrees and side C is 21, unitless. So here we've got 17 and 21. I couldn't tell if on the skills assessment, maybe you didn't have time, or if you just only solved for one of the things, right? But it asked you to solve for A, B, and C. And so a lot of people only solved for the other angle and then left it. It's hard for me to know if that was kind of because you forgot how to do SOHCAHTOA or what happened. So you don't have to tell me, but I'm just saying that a lot of people only did solve for one of the things, and there's 3 things. Okay. So I will start by solving for the other angle, right? Because we know as a rule, all these angles add up to 180 degrees. And so we've got this right angle down here, that's 90 degrees, and then 17. And then that way we can easily find C. So I'll start there and say that C is 180 degrees minus 90 degrees minus 17 degrees. So C is 73 degrees. Okay. If I can avoid it, I wouldn't use this value in my calculations, only because I calculated it, and so I'd much rather stick to values that were given to me, right? And so that's kind of, I don't know, it's just a good thing to keep in mind, right? Use as many of the given values as you possibly can. So because you're solving for all these 3, right? And you can actually figure out what all of them are using just the 2 values that I've given. Right? And so, yes, there are ways to do it, just using values that you've already calculated. But for me, I'm going to stick to the values that were given. Okay. So let's solve for A, just because there's more than one thing on here, so put a little header. So A is the hypotenuse, right? And so I'm looking at sine or cosine. C I know is 21, and so that's my adjacent, right? And so I'm looking at cos x is the adjacent over the hypotenuse. And so I know that the cos of 17 is the adjacent over the hypotenuse A, which is what I'm trying to solve for.
Adjacent is across from?
Adjacent is next to.
Okay, good.
Yeah. Opposite is the across.
Yeah.
Yeah.
Always kind of word.
Did I miss it? Yeah.
I think that makes sense.
Yeah, so this is the hypotenuse.
Yeah.
From B, this is the opposite, and this is the adjacent because it's next to.
The only thing I forgot with this was, so when you're deciding which angle to use, so for cos,
Yeah.
you just use the angle that's the adjacent and hypotenuse angle. So for
Yes.
17,
Yeah.
Is that how you decide?
So yeah, so what I'm doing is because I know this one, right? How I'm deciding which one's adjacent and which one's the hypotenuse, or the hypotenuse is always. But how I'm deciding that this is the adjacent is because I'm looking from the B lookout.
Sorry, like when to decide or to know which angle to use.
Yeah.
You're just going off like cos x is adjacent or it's adjacent over hypotenuse, so you're going on the angle between the adjacent and the hypotenuse.
Good. So then without doing any calculations, we can kind of rearrange this first, right? So we're solving for A, and so to solve for A, we have to get it on one side. So first thing I'm going to do is I'm going to multiply it over to the left-hand side, right? And so I get A cos 17 is 21. I'm moving it over. And then to shake A out on its own, I have to divide both sides by cos 17. And so I get A is 21 divided by cos of 17. And these are in degrees, right? So you have to make sure you're in degree mode. If you're working on this calculator, I found it, where was it? think it was in the setup. Yeah. If you go, there's the menu button up top. If you go shift menu, there's the setup option. And if you hit 2, it's the angle unit. And that's where you can choose between degree, radian, or gradian. I don't even know gradian. Not in like this sense. Maybe I do. And then you just hit the value that you want. So for us, we want degree mode, so we just hit 1, and it should show up as a little D on your screen. Just as a reminder. Okay. So now we can do 21 divided by the cos of 17 is 21 point, well, it's approximately 21.95952689. Okay. I would hold off on rounding for a little bit. In fact, I'm not going to round at all just now, but also because I want to be able to check my answers, right? Because we know that a squared, well, I guess in this case, b squared plus c squared has to equal a squared. I got to switch those around so that they're the same as what we have in our brains, right? A squared plus b squared is c squared. But in this case, it's a little bit different, right? But this squared plus this squared has to equal this squared, right? So, so that's how we can check our answers. You could also use that to solve for the remaining side. That's fine. But sticking to that rule of only using information that's been given to find answers, right, makes it hard. Solve for which? Solve for B. So B is the opposite of 17 degrees. And we've got the adjacent, so we've got opposite over adjacent in tan. So we're just going to use that. So the tan of 17 is the opposite, which is B, over the adjacent, which is 21. Okay. Solving for B here is a little bit easier because we just multiply the 21 over. So then we get 21 tan of 17 is B. And then I like to just move it over. Right. 21 times the tan of 17 is, let me just make sure, yeah, 6.4203, approximately 44311. Okay. Check the answers. Because we can, right? As soon as we can check our answers, then let's do it. In our case, b squared plus c squared equals a squared. Right. The two sides squared, added up, have to equal the hypotenuse squared. I promise, for the next triangle we use, I'll have c on the hypotenuse. So then b was 6.42 blah 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 squared plus c is 21 squared. Does it equal a squared, which was 21.95 squared? Shouldn't make it so sloppy here. I have an equal sign with a question mark on top because I'm checking to see if they're equal. Right. So I've got 6.42, and then I can square it because it's already on my screen, plus 21 squared. I get 482.2208.211. Is it equal to 21.95952689 squared? Phew. 482.2208.212. Close enough. All right. So you just want to check to make sure. Of course, we've lost things in rounding our powers of 2, but that's all right. So, any questions about that one? Okay. The roots. Quadratic equation. Again, it's one of those scenarios where when I'm looking at stuff, I can't tell if you ran out of time or if it just wasn't coming to you, right? The quadratic equation. And so, but there was a lot of blanks. So for whatever reason, there's a lot of blanks. So if you feel like you need more practice, you can look at factoring practice. And as long as you have an x squared and no higher term than an x squared, you can use the quadratic equation. Okay. There's other ways that you can do it too, but for this, we said might be helpful to use the quadratic equation. So the quadratic equation helps us find values of x that make this 0, right? So essentially, where does this function cross the x-axis? Right? At what values of x does that happen? Okay. And so in general, right, let's do a little in general note here. In general, the roots of, what is it? Ax squared plus bx plus c can be found using, here I've got a page break. X is negative b plus minus the square root of b squared minus 4ac over 2a, right? The quadratic equation. So as long as you have something like this, right, ax squared plus bx plus c, then you can use this equation, right, to find the roots. And so it's going to give you two values with the plus minus, right? This, I should make this look like a B, actually. Not B, oh, not much better. It's a B. Luckily, it's typed out, so phew. Okay. So for this first one, I'll just write it out here. We've got x squared plus 11x minus 12, right? And so A is 1, right? B is 11, and C is negative 12, right? So you have to capture that negative in there. Okay. So now we can solve, okay, well, x is negative b plus minus the square root of b squared minus 4ac over 2a. Filling in these values, right? We've got negative b, so negative 11 plus minus 11 squared minus 4 times a, which is 1, times c, which is negative 12. You have to be careful. You can't take the square root of a negative number, right? That's illegal math. So you're not allowed to do that. You can't, in fact. You can try to take the square root. So the square root of -2, for example, syntax error. So it won't let you. And so that's where you have to be really careful with your negatives, right? Because that negative on the 12 is actually what's going to save you here, right? Potentially. Over 2 times a, which is 1. So simplifying a little bit, we've got -11 plus minus, and then in the square root, we've got, where did it go? 121 plus 48 divided by 2. Add 121 and 48, and then take the square root, we're going to get 13. -11 plus minus 13 divided by 2. Okay. How are you going to do this? -11, first you're going to add 13 and divide it by 2. That's one of your solutions. And then you're going to take -11 minus 13 divided by 2, and that's another one of your solutions. -11. -11 plus 13 divided by 2. How am I going to write this? Like this, probably. Divided by 2. And -11 minus 13 divided by 2. Oops. -11 plus 13 divided by 2 is a nice 1. And -11 minus 13 divided by 2, I get -12. Okay. Meaning that this function would cross the x-axis at x equals 1 and x equals -12. Or the other way around if you're super picky. -12, then 1.
Oh, so this just plotted intersect points are two-dimensional. Right?
Yeah.
Okay.
So, yeah. So we don't know what's happening in this function in between, but I know that it crosses the x-axis at -12 and 1. So that much I know. And those are the roots. Okay. So the roots are just where it crosses the x-axis. And thus y is 0. Throw in that little plug. It is curved, yeah.
So those are just intersecting one.
Yeah. There. So here we've got the same thing going on, right? Let's just figure out here. So A is 4, B is 8, and C is -140. Right. Same idea, right? We can kind of kick it up a notch. And so we've got x is -b plus minus the square root of b squared minus 4ac over 2a. Do you have it memorized yet? Thanks. No worries. -8 plus minus the square root of 8 squared minus 4 times 4 times -140 over 2 times 4. Simplifying in there, we get -8 plus minus 8 squared is 64, and then plus 2,240 if we multiply that all out, divided by 8. Which is -8 plus minus 48. Once we add 64 and 2,240 and then take the square root, we get 48. Divided by 8. You could simplify here, right? Because 8 is divisible by 8 and 48 is divisible by 8. But why though? I don't know. I just, you can absolutely. It doesn't really save you any steps though. So maybe one total. Not worth it. So we're going to have -8 plus 48 divided by 8 and -8 minus 48 divided by 8. I get 5 and -7. So this little guy is crossing the x-axis as at -7 and 5. Or 5 and -7. Whew. All right. Any questions about that one? Or any of it? No? Okay. All right. So this is where I was gonna change into the sig figs. But what I want to do now is have you guys tell me what Frank told you. So I'll just make a little end of worksheet. Nice work. Because I didn't actually bring a copy for myself. Do you mind if I just have a look at this? Okay, so looking at these sig figs, you're right, it is 6. Oh man.
Did you copy this one too?
I did, of course, I copy everything. I'm shameless. But it always backfires. Alas. Okay. Spot the knot on the first page. Just reading those rules, yeah. Yeah, in the second box, it should be 6 sig figs. There's not even 8 numbers. It should say 6. Shame on me, but also shame on them. This actually came through 2 people. Slipped through the cracks.
Say that one still.
Pardon?
Say that one still.
Yeah, shame on them. I shouldn't have to look for stuff. It should be ready to go for me. No, you're right. Should take responsibility. So just make sure that you change on the first page the captive zeros example. The first one, there's only 6 sig figs because there's only 6 numbers. Yeah. Okay, so let's go through these and let's talk about what Frank said. So non-zero digits are significant. We all agree on that. They're all significant. Before the decimal, after the decimal. Okay, great. Sig figs. Sorry, I stole yours. I don't know why I didn't bring mine, but anyways. non-zero digits are significant. We agreed on that, right? What was the next thing? Captive zeros between non-zero digits are also significant, right? Still on board? Okay. Captive zeros between non-zero digits are significant. Okay, so far so good. Me and Frank are in agreement. Leading zeros are not significant. How does Frank feel about that? Good? Great. Hey, so we're doing good here. Leading zeros are not significant. How about these trailing zeros where we've got two options? What does Frank think about that? Frankie says, relax. Is he on board with these or pardon? Yeah. Is he on board with these or what?
Yes.
Trailing zeros not significant if they're at the end of a whole number, right? Because they're not captured by anything, by the decimal. They're significant if they're at the end of a decimal. Right. And okay, good. Trailing zeros. At the end of a whole number. Oops, that says whole. Of a whole number are not significant. Trailing zeros at the end of a decimal are significant. Okay. So we're using the same rules in general for identifying sig figs. That is a good thing. I'm guessing multiplying and dividing is where we got stumped. So using sig figs, multiplying and dividing. Okay. The final answer has the same number of sig figs as the term with the fewest sig figs. Does that match what you learned?
I think it's all going to match. It's just the actual recording of our answers for instrumentation purposes.
Oh.
So far.
Mm.
Yeah.
3 sig figs? So then why are we going through all these rules if you're just going to go to 3 sig figs anyways?
Because I think it depends on what we measure too. Because if it's like a million liter tank, we don't want to do 1 sig fig.
No, you don't.
That's what
You rarely want one sig fig. Yeah.
We have to use the rule for like most of the calculations at the beginning. It's near the end and other classes, and like it relaxes, and they don't want to have to look at a very large number. We can use around the.
Yeah. So, but where does that put me though?
That's why I did something here. Where his class is 1 plus 3.
Oh. Oh, I see what's happening here. I'm bad cop. Frank, he's fun dad. Okay. I see what's going on. I see what's going on. Well, so he only uses 3 sig figs.
Eventually.
So can we just use 3 sig figs? That might throw me for a loop sometimes, though. You know, math. Math is tricky. It's just no, it's a frame of mind. I always say math is 80% attitude. That's right. You're doing it. So let's just, I guess, rewrite this here. Mostly because I don't have this sheet anywhere. The final answer for multiplying and dividing has the same number of sig figs as the term with the fewest sig figs. The final answer has the same number of sig figs as the term with the fewest sig figs. There's got to be a quicker way to write that. Where? Addition and subtraction. The final answer is the same number of decimal places as the term with the fewest decimal places.
Oh, so it's not about sig figs, so decimal places.
For adding and subtracting.
Yeah. Well, like,
Yeah.
like dividing sig figs is fine, but that's okay. I got a question on this.
There we go.
Cost me like 7%.
Oh, ouch.
Online
So here, so addition and subtraction, you're going to pay attention to the decimal places. Okay. So the final answer has the same number, oops, number. I always write number instead of number. Number of decimal places as the term with the fewest decimal places. I think that's the rule I apply in general. Usually in my math, I round to the fewest decimal places at the end, unless it's, I don't know, I like to keep at least 2 decimal places, but that's just me. But probably because a lot of the calculations are money calculations. Money has 2 decimal places, typically. Okay, so roots, radicals, and powers. So basically everything else. The final answer has the same number of sig figs as the number. Oh, joy. So it's a root radicals or powers. The final answer has the same number of sig figs as the number. How about if you're combining exact and approximate values, right? So if you're dealing with things like pi and that kind of fun stuff. So the final answer has the same number of sig figs as the approximate term with the fewest sig figs, right? Because how many sig figs does pi have? A lot. Uncountable. Still. It's like to be determined. We'll get there. We'll get there. Great minds are working on it. But until then, right, that's why we have to stick to the approximate value. And so the combination of exact and approximate, bless you, the final answer has the same number of sig figs as the approximate term with the fewest sig figs. And then, of course, as you're going through and doing calculations, you keep all your decimal places until the very end, and then apply the rules of sig figs at the very end, right? Kind of keeping track of how many sig figs you're at each stage. And so I think the takeaway here is it's important for you to be able to quickly identify sig figs, right? And kind of be comfortable talking about sig figs and stuff like that. But of course, I'll try to stick to the rules because I guess it's good. But then there'll be kind of 3 sig figs. Was it 3 sig figs or 3 decimal places? 3 sig figs. Okay. Yeah. Yeah.
I get the 3 sig figs. You don't get worried about.
Oh, sorry. Can I see that again? Oh, thank you. Thanks. So here, so 1 decimal place from the addition. Okay, fine. Because the one with the least number, so, and 3 sig figs. Okay. Mm-hmm. Separately, right? So you want to, so yeah, it should just be 1 decimal place.
Because they're multiplying, so they have that second decimal that's not a sig fig in the next number.
I'm gonna guess that sig figs trumps decimal places. This is what I'm kind of seeing here, right? Because I think what you're saying is, okay, so we decided we can only have 1 decimal, but then at the end, how can we have 2 decimals, right? Is that what you're saying? Okay, so yeah, I think what I am seeing is sig figs trumps decimals, but I'm gonna ask about that.
So for this example, then the 3.9.
Oh,
No, okay.
okay. So
Well, my answer is why is it 3.4? Yeah, the least number is.
You're no longer adding, multiplying, and dividing. You're at 3, 6, 6.
Okay, so.
oh,
Multiplying by.
sorry, can I see that? Sorry. Should I get my own?
Oh, it's just about that.
So let me just see, are they using 15.0 or 15.03 in the division? Or will we be able to tell? 12.034 times 4.2. Okay, 5428 divided by 15. 3, 6. No, so they're keeping 1503.
I think they're showing the full numbers, but still.
Yeah.
It's just because if you're actually doing a calculation with your actual numbers, your whole decimal still has to travel through the equation.
Mm-hmm.
But those decimal points don't actually necessarily matter at the end. So it's just showing that you have the 15.0 as your sig fig still from the addition equation, but you still have to carry that 3 through the actual math equation.
Yeah, I agree. But so isn't this one decimal place note kind of redundant then? Because it just, we ignore it anyways, right? Because, so it kind of brings me back to, sounds to me like sig figs trumps decimals. Because at the end, we need 3 sig figs, right? And I guess, whoa, what would we do if it was, if the 15 was just 15, no decimal places, right? Would we need 2 sig figs at the end? This is not me being like a clever teacher trying to get you guys to think. I'm actually asking, so if you had something like, instead, 50.5428 divided by, let's say, 11.13 plus, or let's just say 4, right? No decimal place, right? Then we get 50.5428 divided by 15.13, right? Because I would have no decimal place, right? So now here, we decided this had 3 sig figs, but now it looks to me like this one only has 2. So the question I'm posing is, does my answer, do I have 2 sig figs or 3 now? That is the question. I'm guessing 2, right? Okay. Yeah. Because then we get, what do we get? 50.5, oops, 5428 divided by 15.13, I get 3.340568407, but for 2 sig figs, But I only want 2 sig figs, right? Or which do you mean? Oh, yeah, and then there's the added component of Frank wants 3. I gotta run this one by Frank, yeah. See what he would do.
Previous slide in the equation for the base, we have like your number
It seems like you keep a running tally. But like I said, I'm just kind of posing this question. So I'm not, something to think about, get to the bottom of. Okay. But I will ask Frank about this one and see kind of if this makes it 2, and then what do we do? Or I guess the problem is just, I don't ask you questions like that. How about that? Okay, you've got some sig figs practice sheets, right? If you want to stick around and work on those, you're welcome to. But otherwise, see you guys on Tuesday. Yeah, sure. Let me just end this here. There.